going to start with this two comments. The sky is actually not the limit because we actually do stuff with spacecraft and Artemis and all that stuff. So, and then I came across this quote from Galileo: "The book of the universe is written in a mathematical language. Its characters are triangles, circles, and other geometric figures, without whose help one wanders in vain through a dark labyrinth." So my talk is going to be broken down this way. I have to frame a reference as to where I'm coming from, and hence I got to talk about Collins Aerospace and their initiatives, and then the Adaption program that we're starting up within the company, the tools that we're building to support them, and then some pilot projects, and then bring it to a conclusion. So Collins Aerospace, it's actually the largest aerospace component supplier on the planet. So if it's in the air, we're probably on it with some device. We build everything from engines all the way to landing gear, brakes, windshield wipers, interior lighting, all the actuators. So we're capable of doing any one of those components. Collins Aerospace is actually one of 3 business units in a larger corporation. Within Collins Aerospace is 68,000 engineers, of which a little over 17,000 are engineers. So people that do what I do, essentially. Our legacy is over 100 years old. We have 300 sites across the planet. And we do everything from commercial aviation to regional to military defense to space, which I mentioned, and helicopters, but also the infrastructure within the airport itself. Our goal, and part of my agenda as an employee, is to help redefine aerospace on a regular basis. So the company has strategic initiatives that they try to drive over a 5 and 10-year period, which includes things like advanced structures, so composite materials, merging physical structures with functionality, autonomous operations, trying to electrify the aircraft from end to end, get rid of the hydraulics. Hence, a few years ago, we actually came out with electric brake systems to get rid of the hydraulics, to reduce weight, compress the size. Connected ecosystems, which implies it's always connected to a network that allows us to gather information on a flight-by-flight basis, and integrated solutions. Because we have all of this functionality, we're finding that we can merge functionality in components, and that pushes us into a system mentality of how we think. Because of those strategic initiatives, the core technologies, everything from additive manufacturing, composite materials, surface technology, machine learning, human interface. The autonomy is actually driven towards taking workload off pilot and crew as much as possible. The digital enablement, which is part of the direction that we go from an engineering standpoint, is essentially go to end-to-end solution, and by that I mean from the conception all the way to retirement of the products, which can be 10, 20, 30 years. It's hence multidisciplinary. And what came out of that is a model-based systems engineering, which is the 4th item there. And the whole idea is that instead of the systems engineers translating their users' requirements into a document to say this is what the system has to do, and then documenting that and handing it to the design engineers, the idea is that you have a model that is the single source of truth through the life cycle of the aircraft. That allows us to do incremental changes to the system without having to design the whole aircraft. That compresses the cycle and the life cycle of the aircraft down by almost a factor of 5, because you can do essentially continuous improvements to the aircraft. So given that position of model-based systems engineering and model-based software design all the way into the testing and beyond, the model is important, which is where geometric algebra comes in. So my agenda is to make that a regular expression of the engineers that do the systems-based modeling. all the way in through the design of the hardware, all the way through the software. So if you take a sort of broad sweep, and this is the motivation that pushed me in this direction, if I look at all the different things that you can do with geometric algebra, and there's several good survey papers that describe this, I just started taking off the things that we do and can use and said, yeah, this is an ideal framework for GA, because our systems are pushing more towards the digital and cyber physical systems. So what's the Adaption program, or GAP for short? So I need tooling, so I spent the last 2 years building up tools, not done with it yet. And the interesting side effect of that is that as I introduce engineers within the company to the GA process, the first thing is, how could you possibly get something for nothing? And then after I show them that I can do it, then it becomes immediately, if it can do that, can it do this? And then I realize that every time they've done that, it's a step up in what they're asking, like an order of magnitude more. And so I go, okay, this is going to get challenging. To do this and to spread it, I need to describe, analyze, and train the engineers. So it's a shift. And some of you are familiar with that you have to unlearn a bunch of things that you learned in your technical or your mathematical approach to things. And that was actually, for me, the biggest hurdle is I had to I'm thinking matrices, I'm thinking coordinate systems, can't do that, throw that away, start over. And I'm finding that's also going to be the challenge as I teach people this. The next leg of this is pilot projects. I'm looking for people that are risk takers, because this is so fundamental down into the bottom that you're throwing away a whole tool chain, you're throwing away years of learning and legacy, but I think it's worth it. And so I've been very careful of which projects I pick and start to push on so that I've got somebody that's really bought into it at this point. That implies I actually work on projects as an embedded engineer for a short term. I try to mentor somebody, I identify somebody in the team. I push them in terms of, I want you to really understand this, because I have two motivations. I want to go away because I have other things to do. And I want to tap you on the shoulders later on to help you with a different project. And so the idea is to bootstrap up that way. And then the last one on the list is engaging people coming out of college, younger engineers that have already got this skill, so I'm not going through this training. Part of my job as a senior fellow is to actually keep my thumb on the pulse of the engineering discipline. So how healthy is the discipline that I lead? I lead the signal and information processing discipline, which means I'm constantly looking across the skills of the engineers to say, are we lacking something? Or are there a set of people that are going to retire and go away? And so I need to start bringing younger engineers up into that. So I do that on a regular basis besides. Tools. You've seen yesterday all the different kinds of geometric algebra, and this is one of these things where this is the selling point. The idea is that I've got several geometric algebras to choose from, and I want to pick the right one at the right scale. And the trade-off is runtime cost, development cost, maintenance cost. But the other side of that is the expressiveness of the language of the algebra you choose. So if I pick a conformal, for instance, I've got a more expressive algebra, but it's also significantly heavier in the runtime capability. What I've seen is that because the algebra is so close to the code, I can document the code in the math directly and use that to describe the code, and that reduces the maintenance cost. So if I need to do a change, I need to go fix something, it's easier to orient yourself in that code. I chose the 2D and the 3D conformal and plane-based algebra. I'm going to be pushed very quickly into some of the others, but that's where I started. And so why two-dimensional? That's part of my strategy is teaching, is I go down a level to say what's a similar problem there, so that they can understand how to think that way in the GA way with the geometric reasoning, and then come back up which is why I'm always doing it in those pairs. So this is the first one, PGA, the 2D representation. You'll be familiar with this. The multi-vector consists of a scalar, vector, bivector, pseudoscalar. The vector allows me to encode lines, the bivector points. I can do the union, create points, create lines, build them up with joins and meets. So a lot of the stuff you saw yesterday, plus the whole list. I've only listed a couple of the formulas for projections and perpendicular lines through points and that type of stuff. So to do that, so Collins actually has a corporate level license for MathWorks, which means every one of those engineers can pull any one of MathWorks tools down and use it out of all of their tools. And so part of the idea is to integrate into that tool chain because it's already used to do a lot of software development and auto coding and formal testing, formal methods to design test, that type of stuff. So I want to fit into that tool chain. It turns out it's a very nice environment to actually build up. So I use an object-oriented approach, which is part of their language, and organize the toolboxes in terms of operators, which is the basic algebra in the center here in the blue. You know, add, subtract, multiply, divide, that kind of stuff. The dual, the reverse, the wedge, and dot products. But I also have a series of ways of creating those objects. And so I didn't implement it as MATLAB as matrix laboratory, so it's arrays, which it does very well, very fast. But basically I created a new type within MathWorks, within MATLAB. In this case, it's actually the object type is PGA 2D. And so that means I need a whole series of methods to come in from legacy representations of things into the PGA 2D environment. And I have to visualize it so it automatically plots. It can create latex equivalents to any of the multivectors, that type of stuff. It implements sandwich operators. Some of this stuff is not necessarily needed as you become more versed in the algebra, but I want to codify a set that's self-consistent because there are choices within the algebra of how you choose things. For instance, in the conformal, how you define your origin and your infinity could be a designer's choice. You could use a different scaling for the metric and normalizing your points. And so I wanted to fix those. So use these. You can actually call them, for instance, to go from an Euclidean point to a conformal point so that it self-consistently works throughout the whole set of formulas. The next one up is the 3D equivalent to that. So now I've got a longer multi-vector, but again, all of the same. I can map Euclidean points, ideal points, i.e. a point at an infinity or a vector, lines, ideal lines, planes, and do all of the same meets and joins to either go up in dimension or down. So all that's there. So this also has a toolbox. Now the number of operators and functions that are methods that are put in here are much richer. And each one of these toolboxes has a live script, if you're familiar with that. So you can script your functions, but you can also live script them so they're interactive. But you can also put in LaTeX equations and that type of stuff embedded in with it so that you can describe it mathematically, look at the code directly. And so these toolboxes are being built up with all of that support information. Then the 2D conformal, again, more expressive power. Again, another toolbox. So I've kept these separate right now, but I've actually, don't remember who talked yesterday about Chris, I think it was. I want to be able to switch between them, and I've actually been trying to think of that, of how to go about doing this. I've already refactored the toolbox at least twice, and I may end up doing it a third time. And here's where you start seeing the expressive power of not only points, point pair, lines, circles, planes, spheres, but all of these other things that you can encode. So now I've got an explosion of the amount of code that it takes to do this. Just to give you an example, so far, so this code for the 3D CGA, even though it's probably about 90% done, It's 1156 lines of code. It's very dense, and most of that is in the plotting routines. Okay. So these are a set of graphics of the join operations going from points. These graphics were actually created within MATLAB, and I just pasted them in here. Going from points, joining 4 points to a sphere, throwing one of the points off to infinity to get a plane, throwing away that point to get a circle, joining 2 points with infinity to get a line, and you can walk down, and then the reverse being true. Higher dimensions start meeting them and working downwards. So the intersection of two spheres is a circle, the intersection of a circle and a plane is a point pair. So all of these operations are already built into it, and the ability to plot them, just as they're showing here. So then let's go to the documentation. So I described the live scripts that come with these. The next level, which was, and I picked this up from the SciGraph, the cheat sheets, like these. I found them very useful for a number of reasons. I'm trying to orient somebody into what exactly is the expressive power of this. So even though a lot of the formulas, once you recognize the pattern, you say, oh, this works with any object. When somebody's coming into it at first, they're clueless as to that. And so having these kinds of cheat sheets to have them go look does two things. I use it as a training tool, but I also use it to set up test scripts. And one of the techniques that I discovered was, if you're familiar with the tautology, an equation that's always true regardless. So for instance, if I take the various grades of a multivector and I project each one into a variable and add them back up, I better get the original multivector. So I'm constantly looking for those kind of equations that are essentially the identity, because that allows me to test whole swaths of the code with basically random inputs. And I know that this identity equation holds, so I can fairly quickly identify something went wrong. Now we get into the pilot projects. So I spent almost 3 years waiting for the right projects to show up, and then everything started coming together. And so I'm going to go over 4 of them. There are several more in the queue. Inverse color blending problem, a pressure-based fuel gauging problem, a range-aided cooperative navigation problem, and a pick and place or precision alignment metrology problem. So these are all real projects within the company. You have to understand the time scale. So I'm on the front end of this project. I normally work at the R&D part of things, not on the product development half of the cycle. And that cycle could be anywhere from 5 to 10 years. And so when we start something, when I catch it after it's started, that means by definition I'm on the next cycle, which means 3 years later, what I'm designing could end up in the product. And these are all within that realm. What typically happens is, as the person actually doing the current version of it realizes what's going on, they start asking for the tools to help them design the current version so that it doesn't have to have the certification level necessary for flight worthiness, because it'll be verified in other validated in other processes. But that allows me to loop back on the next gen and bring it through as the tool of choice. So inverse color blending. Color is a psychophysical phenomena. It's a perception. By that I mean that so for instance, different wavelengths of light have color, but your perception of that color is part of the mind, not part of the attributes of the wavelength. Okay, which means that you have to actually have what's called a standard observer. And this is years of work in terms of looking at two colors and saying, are these just noticeably different? And then scaling them out. And when you do that kind of experiment with thousands of people, you end up with this surface, which represents how color, the shape of the color. Okay? And years ago, I was trying to figure out, how do I represent this in an algebra? And I'll talk about that a little bit. So what's the motivation behind this? We have an interiors division that does all the lighting and the seats, and part of that is shifting from incandescent to LEDs, and you want to tune the color of the LED to a specific color. And so given a sequence of a small card with a half dozen different colored LEDs, how do you adjust the power on each of those, knowing their wavelengths, to get the target color that you're trying to get them to perceive? Okay, and I refer to that as the inverse color blending problem. So, but to do that, I have to go the other direction first. Given two wavelengths of light, how can I mathematically describe the color I expect to be perceived based on the intensity of, say, two sources? And I refer to that as the forward problem. The inverse is, given the sources of lights and the ability to shift their luminance, which set do I use on those in order to hit the target color? Because you may have a combination that this will run hot because some LEDs are less efficient than others, and so it'll wear out the card faster, and so you want to adjust with other LEDs to pick up the difference, to hit not only the chromicity of the color, but the luminance levels, how bright is it? And the ultimate goal is I want to optimize. So given, am I trying to longevity of the pixel, or trying to minimize the amount of power that's being used, whatever. So I need that first two frameworks in order to solve the optimization one. This was a very old problem. So back, I realized when they approached me and said, "Can you solve this?" I had actually been working on this 23 years ago. And it was a hobby of mine at the time, and I actually came up with a quaternion solution, decided it was so ugly that there's no way I'm going to publish that. So when they approached me and said, "Oh, gee, I could do that in a two-dimensional projective geometric algebra." And this is how that works. So PGA, if you remember, has the 2D version, has three basis elements, the generative basis, two of them squared to 1, one of them squared to 0. I can take the color definition, which is the CIE definition of the color, and I can take the chromatic coordinates, which is where is it on this plot, and I can put that into the E20 and the E10 components. So this represents a point in that plane, and then I can use the luminance level and map it with a weight. And now, just taking two of those, I can add them up and go backwards and extract out the chromicity and the luminance. So how can I use multiple colors to get a target color? There's an effect called the metameric effect. So I can pick two, so this outer edge of this horseshoe shape represents the perceived color of a particular wavelength along that curve. So everything from blue into the red. Okay? If I pick two colors and the target color is between them, that means I can do a weighted sum of those two and reach that color. But that means I can pick a different two colors and still reach that same target color. And that is the metameric effect. So I can literally have two different wavelengths in one eye from the other eye, and you'll perceive the same color in both eyes. So now the question becomes, given a series of LEDs along that plank edge, the different wavelengths, what's the right balance to get to the target color? And it turns out there's actually three ways to go about doing that. One of them is a stepwise process. So I've got three LEDs, P1, P2, P3. I take P1 and P2, create the line between them, take the point P3 to the target, create another line, find the intersection. The ratio of those along each of those is essentially the relative power setting of each of the LEDs. You can also, so that's one way, you can also solve it slightly different, and it ends up being, it's referred to as the triangular method. So if you have a triangle where I have those three and the target color, it turns out that the beta 1, which is the weight on the first one, is literally the ratio of the area of the whole triangle versus the area on the leg of it, so in the lower triangle in the P1 case. And that's a well-known formula, which is fun that it replicated that exact one in maybe 5 lines of math to do that. There's also a third one, which is actually using ideal points, essentially going from the target through each of these LEDs, and you create points on the celestial sphere or on the ideal circle. And you can look at the weighted ratios of those and compute as well. So there's actually 3 ways, and I'm still trying to decide which one I want to use. But for instance, this first one, well, that's 10 lines of MATLAB code to solve that problem, which is that code actually in the corner there, of which 4 of those is mapping from chromicity to PGA, to the conformal space, or the projective space. So this was the one that I actually started with, and it was a conversation with, they were describing how they were going to solve it, and I said, I wouldn't do that, I'd do it this way. And that was where I got the first comment. It sounds like you're getting more for something, how could that possibly work? And I said, yeah, no, it'll work. And then a couple months later, I was handed a charge number and said, go try it, we don't believe you. Here's the number. So I did. So the idea here is that currently the fuel gauging is done with the capacitive sensors, and they're uniquely designed for a particular position in the aircraft. So you'll have 3 or 4 tanks, and each tank may have 3 or 4 sensors in it. And it has to be designed for not only that aircraft, but for that location on that tank on that aircraft, so they're all unique. Okay, and it has an added problem is that as the fuselage of the plane becomes carbon composite materials, it has less shielding power from lightning strikes, and so don't want electrical connections going into the fuel. And so there was a big push to say, can we change these out to something else? And so this is based on using fiber optic to actually drive the sensor, and the easiest sensor to drive is a pressure sensor. Well, Stefan's law says that if you got a sensor, the red dot, PF, in the fuel and another one in the ullage, in the airspace, the pressure differential is related to the height of the fuel. So now you start to see some of the geometry that's going on. And so the question is, can I get it down to those 2 pressure sensors in a tilt, because the airplane could tilt and the fuel line plane cuts through it different, and can I solve for this problem? Turns out you don't need the tilt sensor. You can actually just use 4 pressure sensors in the fuel, not in the same plane, and you don't need, because you can compute the tilt from that. But this is the cheaper number of components. So, being able to implicitly compute the volume of an implicit mesh is where I started from. So because we're helping design these tanks on a regular basis, anyway, we already have the mechanical drawings for the tanks. And so it's as simple as use your design tool and give me the inner mold line, a mesh at a high enough resolution. So this is an example of a wing tank. And I'll pull it in, I'll convert those into projective points. And now computing the volume is essentially this one equation, which is 5 lines of code. Most of it for the for loop to do the summing. Then the question becomes, where's the fuel surface? Well, it turns out it's this 1 line of math, which is 2 lines of code. And I'll explain this a little bit because it's not obvious. So I've got a point in the fuel tank, the one in the fuel, and I've got a height, and I've got a pointing vector from a tilt sensor. So I take the pressure in the fuel tank, add it to the height multiplied by the pointing vector that gives me a point on the fuel surface. That equation is essentially represented here. If I've got a line and a point, I want a surface plane perpendicular to that line that includes that point, and that's exactly what this equation does. Now you also run into the question of, I want backup sensors, I want redundancies in there, so you're going to have more than one of these in the tank. How do I average those, whether it's simply a sum? And so this becomes almost trivial to solve because of that. But I haven't quite solved the problem because I've got this fuel plane and I've got the tank mesh. I have to cut through the tank mesh with the fuel plane. And so it turns out that The 2D PGA is an oriented space, which means I can actually compute on which side of the surface am I in if I have a point. So you take the entire nodes of all the points of all the meshes, figure out which side of the cutting line plane it is, throw the ones above it, take each triangle that is cut and split it into 3 triangles, because every triangle will be either a triangle on one side or the other, or a quadrilateral on the other, and split that one and go from there. And this ends up being the most complicated part, which is about 30 lines of code. So that is where that's at right now. Oh, by the way, that's where this addictive behavior, as soon as I showed I could do that, the very next question was, can you do it 1,000 times faster? And it's like, well, I already know that I can run it in milliseconds. Why would I, this is not the space shuttle where I'm emptying entire swimming pools that fast. And they're like, no, I want to go back through flight data that we've already gathered. And I want to analyze it in non-real time, meaning I want to go through 6 hours of flight in a couple hours. It's like, okay, so now I get into the problem of how do I speed this up? And I said, well, how much faster do you want? And they said 1,000. So I this is one of these, I refactored the code and got it to 600 times faster. And I know how to go to the rest, but that was good enough for them. So the next problem. So if you're I'll phrase this in a 2-dimensional, but in terms of taxi cabs in the downtown area, but it also applies to aircraft. As you go in between buildings, you lose GPS. So you augment that with inertial sensors, 3-axis gyro, 3-axis accelerometer, and just raw integrate the position and the attitude. The problem with that is that any noise is accumulated because it's a unstable set of equations. So if you put noise into it, it diverges from the right solution, which is why they use GPS to knock down that error and to keep it bounded. Well, if I'm driving between buildings and I lose my GPS, now my position starts to diverge. And because we're talking about, for instance, in a car, very cheap sensors, it diverts very fast. Even on an aircraft, a fully inertial, meaning not aided, is usually rated and it'll be off a mile after an hour of flight. And that's a pretty decent one. They're getting better as time goes on, but you're talking a very expensive piece of equipment to do that. And so the idea is that if you've got 2 navigation systems, but I know the range between them, I can use that ranging information to aid both of them. So one of them may be privileged, as in he's got a full solution with a GPS aiding on it that's locking his answer down fairly tight, but the other guy's in the urban canyon. But if they can communicate with each other through a radio connection, you can actually time that and figure out what the distance is. And so the question is, if I have a series of these vehicles that can all communicate and I can give you distances between all of them, can I come up with the topology of where are all the vehicles and use that to upgrade the navigation solution of all the vehicles in that mesh? Okay? But that's called the distance geometry problem. So I've got a series of ranges, and I have to figure out what is the topology that meets those ranges. And then once I've got the topology, now I can best fit it to the navigation solutions and tell me and estimate the errors of each of them, and then feed the navigation filters that error correction. So distance geometry problem, point alignment problem, and then the final one is the data fusion through a Coleman estimator. Okay? I'm going to take on just the first part of that in this description. Right away, if I don't have a fully connected mesh, as in, for instance, if I have 4 vehicles but I don't have 6 connections, I lost one of them, by definition I got an ambiguity because there are 4 solutions. Okay? And so what I want to do is some way of using I want to find those 4 solutions, and so that's the branching process, and then I want to trim it based on which one is the closest fit to the actual nav solutions before I do the point alignment. And this is where CGA becomes very important because of the fact that it represents circles or spheres. Okay? So in this example, the way I do this is I start with pick a vehicle as the self. Each of the vehicles does all of this. You could actually make them communicate with each other, but it's easier just to do the timing between the vehicles and let them solve it themselves. Okay, so if T represents the actual position, I've got a drift error, so the navigation solution is the P, but I've got ranging information that's considerably more tight than that. Because I may have a position error that's measured in multiple meters, but I may have a ranging error that's measured in a foot. Okay? And so my ranges are very accurate. And so the question becomes, so I'm going to anchor myself. I'm going to say that my mesh is located with me, whatever my nav solution is. I'm going to orient the first leg to the next vehicle. I'm going to draw a circle. I'm going to project it back down to that circle for the range. And then I'm going to start walking my way through all of the mesh, identifying. And what you'll notice right away is that you'll end up with a situation like I show in this bottom graph where I've got two circles and I've got two possibilities. That's the branching. But only one of them is going to be within the other guy's navigation solution. And so I can throw away the other one. Now there are pathological situations, like if they're all driving down a straight line where that becomes difficult. But that allows me to trim this down as I'm going. So for 3 taxis, that's 26 lines of code in a 2-dimensional case. And I can do it a triangle at a time, so I've got a complete mesh. I can walk through all of the connections. And then lift that up to 3 space. Instead of intersecting circles, I'm intersecting spheres. Same thing. Now instead of 2 points where the circles intersect, I've got a circle, which are all the possible solutions, and I can walk it again. And this becomes even more difficult because you can have meshes. If you're missing certain links, you think the mesh is rigid, but it isn't. It can actually rotate around hinge points. And so the pruning becomes a little bit more difficult. Okay, so that's how I'm using it for that, to aid navigation. What's the long-term motivation for that in commercial aerospace? The number of people that are going to be stepping foot on an airplane for the first time is going to triple in the next 20 years because of the sheer number of people coming into middle class. That means the airspace is going to be packed to deal with that volume. Right now, for instance, to fly across the Atlantic, you have to have a separation height and a separation distance in order to account for navigation errors. And the idea is that, well, if I'm already trying to communicate to bring that in, I'll just use all the navigation systems. And that allows me to compress the number of airplanes in the same volume of airspace. So now we get a completely different. So we make high precision imaging systems. Our company actually makes the main infrared sensor on the James Webb Telescope. When you start talking about that size of a pixel array with the size of the pixels themselves, the physical alignment of the photo array with the mechanical adjustment when you mount it is very, very tight. And so to automate this system, you're going to place the photo array in a workspace, the mechanical housing for the lens in another space. You got to measure where it's at, pick it up, measure where the mechanical assembly is, and then place it in 3 space with path planning so you don't run into structures, and then hold it there while you bond them together. So that's the motivation behind this. So I got to be able to measure points, lines, planes. I got to be able to path planning to do collision avoidance. I got to clock it so that I align it right. All of that. When I showed this to one of the guys that was actually working on this system, his comment was, "You just obliterated 2 years of my work." So he caught on. Gee, I'm going to tap him on the shoulder and say, "Gee, do you want to work on this? I want to teach you this." And right away I ran up against this problem of the techniques that are currently used are they ignore the geometry. So if I'm trying to, for instance, best fit a line, you take a bunch of points and you create a matrix and you do an optimization on it, but it ignores the very fact that you can choose your measurement points and use that to your advantage. And so that's outside of the algebra, rather than have it part of the algebra and part of the solution. And so my approach was, well, okay, if you're trying to figure out, if I got a bunch of noisy point measurements in 3-space, the optimal solution is to average them, because that drives down the mean error, and the more points, the closer you get, the smaller you get your error. And I want to lift that up to the other objects. Well, it turns out, gee, you can do that. So for instance, if I have noisy point measurements across the line, and if I just randomly pick them in pairs and create lines and average the lines, now you can't just add them, because if you add 2 lines in this space, they're not a line, it's a bivector, but you can throw away the non-Euclidean part of that, and you end up with the average line between them. And, the other thing is that the weight of the line is a function of the distance of the points used to create it, which means it automatically weighs when I have 2 measurements far apart versus close together. So when I start averaging them, it properly weighs them based on what do I expect the error to be, okay? So this one on the left is just randomly picking points and pairing them. But it actually ended up being very close, and I'm still trying to figure out why. But then I said, well, no, let's take ones from opposite ends of the lines and build them that way. Well, it converges much faster. But it begs the question, how does that compare to the classical optimization techniques, which don't take into account this kind of thinking? And then the same thing for planes. If I have just a bunch of random points in a plane and I take triplets and create the planes, you end up with this green cloud of planes. Averaging them, it actually ends up being fairly decent. But if instead I say, no, let's be a little bit more logical in how we do this. Let's cluster them in different areas and pick up the triplets that way. And it converges much tighter by just summing up all the planes, renormalizing it. The path planning, this is where I think Joan's stuff was, I want to be able to create coordinate transform because I want to do a blind connection. So I'm measuring a plane because I know what's on the other side of it. I want to do a blind connection to it, and I have to align it, and I have to clock it correctly. Well, being able to basically take these lines and planes that I've just measured and compute the transform, and then basically interpolate or break it up so I can do path planning. And so that's where all this comes in. So those are just the first 4. I got 3 others that are in the queue. I briefly mentioned path planning. As you go into more autonomous flights, you have to constantly think of, if something goes wrong, where should I land? And redesign your path, or for instance, you're flying into a storm front and you want to go around it. There's a whole art and science behind how do I reroute this aircraft to avoid a thunderstorm. Okay? And so the first question is, do I have the fuel and can this do that? So if I have to clear a canyon, can I actually clear it with this airplane? And so there's a whole validation of flight path process that goes on. So that's another one that's coming up, which ends up being a 3-dimensional, it may end up being space-time, but not relativistic, because I need to know where I'm at a given time, because I may have a collision in space, but he got there an hour before I did, so I need to adjust for that. And so all of those questions, so that's another kind of problem that shows up. So first thing I discovered, which was mentioned, there are all kinds of different formulas. In fact, there's an age of some of this stuff, so you got to be careful. But that means that I don't have a complete set of formulas end to end. Remember I said I wanted tautologies, so I can map it all the way through to know that this system is self-consistent, given the design choices I've made in the algebra itself. And so having tautologies and a complete set end to end is very important. And that means things like, so I have a 1920 engineer's black book, which is just a list of formulas. And I know enough to go look at this and say, oh, I didn't know that the power of a stack was related to the fourth of the height of the stack. The curiosity makes me go look to find out why, but I'm trying to get something done. So having something that's literally a reference book, but not a teaching book, is important. And that's where the cheat sheets come in handy. It's a version of that, essentially, taken to a book form. Much like the Kalman filter domain, where you're doing estimators, there are actually two separate sets of symbols that are used. And you have to know whose set you're using, because it's the same variable names, like K or X, but they have completely different meanings. And so trying to avoid that as much as possible. I had to make a choice early on, because I was looking at all the beautiful languages that are available that have implemented GA, but I needed something to go into MATLAB because I already have them trained in that. And so adding a new programming language on top of the GA was just a bridge too far. Plus, I needed to fit into the tool chain itself. So a number of different challenges. So my next level of effort is, we have an internal university. Remember I mentioned that we maintain the discipline health of the different sub-disciplines within engineering. And so we actually have a whole team of people that help us design coursework and videos and training materials. And so I'm leaning into that part of the company to set up what's called the Collins Aerospace Technical University, to start creating training materials for the engineers. I have to design not only courses, but entire curricula in this area, because I have to go from how to use MATLAB for a novice to all the way through how do you auto-code this. One of my forward-looking goals is that we do a lot of stuff in Simulink, because we do what's called the in-the-loop simulations. You start with a model of your design inside a model of the aircraft, or from a control standpoint, the plant model. What are you trying to control? And then once you've validated your model works in that system model, then you move to a software in a loop where you auto-code it and link it back in to a processor in a loop where you're running the plant or the aircraft model, but all your code is actually on the target hardware, all the way up to a hardware in a loop, where now I've got an embedded piece of software in a piece of hardware in a larger simulation. And so we've got several flight simulators in the company. That means I need to get through all the auto-coding stuff, all the optimization for real time, and I need to have that tool chain qualified for flight worthiness, which is a whole nother level of how you validate that your compilers actually do the same thing every time and do what you expect. I'm starting to see a need for higher level geometric algebras. One example would be formal methods to know how many test cases will it take to test this piece of code. So every time it branches, you've got another test, but it's cascaded in the logic within the code. And so being able to say, given all of the sub-branches and branches, what is the minimum number of tests that cover all the branches? Well, at first, you'd say, what does that have to do with geometry? Well, it does, because every branch point you can think of as another dimension, and I'm either to the left or the right of some point on that dimension, which means the problem is really taking this, let's say I've got 20 branch points, 20-dimensional space, and breaking it down into polygons, planes, and figuring out, can I get a point on all of the mutually exclusive areas that are separated by one of these planes? And so that immediately pushes me into an n-dimensional PGA, where the n is how much branching goes on in this code. So it'll show up in that as well. And that's the end of it. Thank you.